So it's
okay. Then okay, then let's continue with our EEG course. So you have seen, or it's with new cognitive methods in programming. So you've seen I've changed the schedule a little bit given our discussion that things are might a little bit more tricky than I expected. I will do, of course, we will finish our EEG course. So we will do now 2 more sessions on EEG. One devoted to source-based analysis and the other one to frequency domain analysis. And after that, in this class, I will show you the SPM data analysis by means of programming, so not the GUI stuff as we discussed, but then I thought that's really too boring, and actually I also showed you some of that actually in the beginning of the statistical methods course. So I think we can use the time a little bit more valuable in the sense that I show you how to program scripts. It's relatively straightforward, but then nevertheless I show you that. That also means that there will be no open science aspects in this course, which is then the case, but maybe it's also more important that you first learn how to do science and then do open science. Although it's actually fairly important. That's a question.
Do you think that you'll do this open science course in the next semester or sometime next year?
That's a nice question, because that leads me to the next point. So what we will be doing is there will be a summer school, the Oxford Berlin Summer School, which basically Ulf from Quest is organizing, and I'm contributing as part of Freie Universität Berlin, and that will be in September. However, I think that's only for PhDs and postdocs. So I think you, if you're 1 year or 2 further, you can participate there. I think we will also make the stuff, of course, available online. So in the master program, I think these open science aspects then are not integrated. So it depends a little bit on how things go further, but essentially no. But there are, I'm still doing the summer school, and in principle, this could also be open for SCAN people, although it should be only for PhDs. But let's see. It's the first time that Ulf is organizing this. It's the first summer school anyway, and Ulf is always very optimistic in terms that there will be millions of applicants. But also from our other open science experience, I noticed that maybe it's good to have the SCAN students to fill the rooms. So let's see. Maybe that's an option. Otherwise, this stuff is it's more an attitude. The whole thing, the whole open science business. I'm getting a little bit tired of teaching open science stuff. Not that I'm really tired of teaching open science stuff, but it's just do it, essentially. Yeah, and go to labs that share their code. Try to share their data in accordance with the data protection regulations, and in general know what they are doing. That's the more important thing. Anything else about the course outline? No. Good. Then let's enter the last phase of the EEG course. Again, as I said, devoted to source-based analysis and frequency-based analysis, which kind of can view them as on top of the ERP research if you want. So you can basically think about the stuff that we've done so far. That was kind of how EEG, ERP research started and went on through the 50s to 80s maybe, before computing power increased a lot and a lot of things were possible that weren't possible before. And source space analysis and frequency analysis are then stuff that reflect a little bit more modern EEG research. However, like with the whole computational modeling business, if you do an EEG experiment, it's a good starting point to first look at the event-related potentials, to have a feeling that you reproduced some of the effects that have been reported previously. And then if you want to do something in addition, you could do source space analysis, so ask where the cortical origins are of your observations, or you could do frequency analysis if you believe that the brain is made of many sine and cosine oscillators, or you could do computational work if you believe that in the EEG you find trial-by-trial variability that might be of interest. And we're looking at two of those, source space analysis and frequency analysis, because they are much more common and they don't involve anything that would take a lot of time to explain. And we start with the source space analysis. So the fundamental idea of EEG source analysis is to basically leave the electrode level, where we've now seen that we can compute event-related potentials, and ask where in the brain does this activity that we see on the scalp arise. And this is of course very close to the heart of neuroimaging people, because especially if you got into the field because of these pictures from fMRI that you've seen, where you see the brain and then you see some blobs of activations, then you have the feeling that you want to know where things are coming from. Whether that's really important to understand the function is a different question. So EEG source analysis is close to the heart of every neuroimaging practitioner. So knowing where things come from. It is somewhat dominated, and this is also something you realize once you look into the methods, by engineers. So for some reason engineers took part of a lot of the EEG source analysis business in kind of the 80s, 90s, 2000s, which then sometimes leads to the fact that it's not that easy to understand, because engineers have their own math, which is even worse than the math by physicists, so that you don't really know what they want to tell you. But everybody loves engineers, and they have done a great job in actually getting the whole EEG source business to start. Now there are a couple of, I'll just start with the whole business. So there are 4 things that we want to talk about, which are listed here. The forward problem of EEG source analysis, which concerns the questions how you get from a cortical activity to an observation at the electrode level on the skull. Then the inverse problem of EEG source analysis, which is of course the inverse of the forward problem. So how to get from EEG activity on the scalp, that means in your electrodes, to activity at a cortical location. So these are the basic problems that we first want to discuss. And then there are 2 main approaches that are being used, namely equivalent current dipole modeling, maybe these days a little bit less, and distributed source reconstruction maybe these days a little bit more. I think equivalent current dipole modeling may be a little bit on the decline. However, if supported by biophysical models of neural activity, which in neuroimaging come under the label of DCM, equivalent current dipole modeling is also well alive, but the pure equivalent current dipole modeling may be a little bit on the decline. Good. So forward problem and inverse problem. That's the first thing to talk about and the first terms to study. What you should keep in mind with the whole thing, especially in source analysis, that source analysis starts essentially where we stopped talking about ERPs. So the assumption is that you have computed event-related potentials, that is voltage deflections over time, for each electrode. So here a little bit small in terms of access labels are 64 electrodes with the standard labels, as you have memorized all of them now. That was a joke. So here are the electrodes. So that's essentially space, but electrodes. So not a Euclidean space or something, but electrodes. And this is time, and you see the voltage deflection in each electrode. So this is where the whole source reconstruction starts. Yeah? So there is something like that. You have computed ERPs, and now you want to use this. We've seen this also as kind of movies. This dynamics of the topography of voltage deflections. You want to somehow make sense of that from the question of where this is coming from. There are two problems, and there are many reviews also that you can use to learn more about this. One is the forward problem, which, a little bit more formally than what I previously said, is the evaluation of e.g. electrode potentials given known cortical source activities and volume conduction properties of the head. So the question, and this is a physics essentially problem, is if you have in some point in 3D space electrical activity, and you know that the space surrounding this source conducts the electrical activity with specific properties, so maybe more, maybe less, maybe this whole thing has a geometric shape that is interesting. What is the electrode potential that you would see at an EEG electrode? That's what's called the forward problem. And as previously stated, the inverse problem is then the evaluation of cortical source activities given the EEG electrode potentials and volume conduction properties of the head. And what you also should keep in mind, in general, at a single time point. Yeah? So if you look at again at this matrix, then what we just said, the forward and the inverse properties, they refer to a single slice here in time. So usually the assumption is that there is no delay in terms of the electrical conduction. It might be dampened or heightened and have its way through space, but there is no delay in terms of the source activity happens, and 10 seconds later you see it on the electrodes. That's not the case. And there's also not the idea that the conduction properties change over time. So the brain on these time scales that are of interest in EEG is of course constant. So the forward on inverse problems you can view just for a single time slice through this. And if you just concatenate then all the time slices, then you have some cortical dynamics as you have them on the electrode. So another visualization and another explanation of the whole thing, kind of graphical manner. So the idea is that you have some dipolar activity according to our very basic standard model of EEG source activity that we discussed with the pyramidal cells that are all aligned. That extends, of course, in terms of its electrical properties over a space. And the question is how or what of that is projected to the scalp, known as the forward problem, and what is once you, and in this case, for example, here you have this dipolar pattern where you have a negative source, negative dipole side here and a positive dipole side here, then of course you would somehow think that this is of course leading to negativity on the scalp here and positivity on the scalp here. Now if this thing of course would change its orientation, things would change. But then going back from that, if you have this scalp topography, something negative here, something positive here, what is happening in the brain? And we will do this fairly semi-mathematically, but with a little bit of pseudo-math or whatever. So the important thing is that we talk about 3D space. So an activity within the brain, and this is now the parameterization of the dipoles that we learned about in terms of pyramidal cells. An activity in the brain is described by 6 values, 3 of which are the position. So that's essentially where the activity is located in 3D space. And 3 others of which are the moments in X, Y, and Z direction. It's not really shown here. Essentially there is one error representing this activity, and if you project this one error on on the 3 axes, then you get these moments. So essentially you can think of the moment values as the activity of the dipole in the X direction, the Y direction, and the Z direction. I'm not quite sure why I drew it so tilted here. So I should have drawn an arrow, and then the moments are the ones that are projected on the axis. A little bit of a confusing image. And then there are different ways one can do such source reconstructions depending on whether one fixes both positions and moments or not. And this is exactly already what the next slide shows. So in the equivalent current dipole approach, one starts with the idea that there are few sources. So let me show you this in a little bit larger. Still quite small. We will see better examples. So here you see some dipoles, but there are only very few. There are like 3 or 4 that are to explain. Here you see it better maybe. You don't see anything. There is a dipole. We will see that larger. And this dipole varies in activity over time and tries to predict this cortical topography, here shown a single time point. Usually in equivalent current dipole approaches, both the positions and the moments are estimated from the data. The second approach, like I said, that is maybe a little bit more prominent these days, are distributed source reconstruction, here with a kind of interesting picture where instead of having a few dipoles, you basically put dipoles over all cortical locations. So for example, if you have a cortical reconstruction and you put dipoles everywhere on the cortex in kind of this in this orthogonal manner, like you think about the pyramidal cells, then you would have many dipoles. You know where they are because you put them there, and you just have to estimate their moments. We will see that again. So these are the 2 main approaches, and both of them, only that this gets clear, both have a forward and an inverse problem. The forward problem in both cases is well defined in the sense that if you know what's going on inside the brain, then you can compute and predict what's happening on the scalp. The other way around, if you know what's happening on the scalp, it's not necessarily clear what's happening inside the brain, because you can have multiple configurations of, for example, dipoles or distributed sources that explain the same scalp topography, and you have what is known as an ill-defined problem, which then requires some constraints to actually be able to estimate a solution. So yeah, let's keep it at this. So this is a general overview. We next go more into the forward problem and then the inverse problem. Questions so far? No? So first thing then, solving the forward problem. Yeah. So that's why this is called forward problem solutions. In the EEG literature, you usually, this is somehow swept under the carpet, the problem of the forward problem, because usually the software solutions that are available have kind of standardized way to compute these forward problem solutions, and then it's not much discussed, and also because of its well-defined nature, it's not something that depends too much on the user interaction, for example, deciding how many diagrams to use or what kind of constraint to use for source reconstruction. So this is sometimes why it's communicated in EEG methods articles that it's fairly simple. It is simple once it's solved, because then it's just matrix multiplication. But in general, what the forward problem entails is solving Poisson's equation for current density dipoles. Lena, do you know what Poisson's equation is? Have you heard it? You forgot it. Yeah, that's this. This is. Otherwise, it would be weird if people with a bachelor not in psychology knew what they actually learned in their bachelor, because psychology students always say, if I ask them, what did you achieve with? Yeah, I heard it, but I don't know what it is. And now if you ask other people, that's the right answer. So you should say, I heard it, but I don't know what it is. Sorry. So Poisson's equation is essentially it's in the big canon of Maxwell equations. It's a partial differential equation that it's actually a second order partial differential equation that allows you to evaluate, or it defines an equation for the potential at a given location in space, given that you have an electrical source somewhere in space. So that's something you can compute. I at one point had the formal stuff in here, but now I think I've taken it out completely. So it's a differential equation, but it's not only a differential equation, but it's a partial differential equation, which you need to solve to be able to evaluate the potential at a given location in space, knowing that there is an electrical source at one point. And these kind of differential equations, in this case partial differential equations, can be solved either analytically, meaning you have some tools at your disposal, meaning in essentially your head or on Wikipedia or in books, that allow you to do some manipulations, integrations, or whatever, to show what kind of function follows from a given differential equation, or you do it numerically. And actually, the analytical solutions exist for spherical conductor head models. So if you assume that the head is a sphere, then you can actually compute the potential based on this equation for a given source. However, then of course, neuroimaging people would say, yeah, but the head is not a sphere. So one can solve differential equations also numerically for more realistic conductor head models, and there are two things that you will always come about in brain imaging literature. One is the finite element method, and one is the boundary element method. So that's essentially, I think it's an option that you can choose when you do an EEG source analysis, for example with SPM. You choose finite element or boundary element, and they are different numerical approaches to solve Poisson's equation. The finite element method partitions the head volume into a large number of cubes, and then assumes that these cubes are homogeneous, and computes essentially the potentials over these cubes, and can then of course build in different tissue types based on, and there are different conductance properties based on these cubes. The boundary element method, which is usually faster because it's simpler, assumes that the conductance inside the brain and the skull and the scalp is homogeneous respectively, so it's not the same between the brain and the different tissue types, but within them it's the same. And the only thing that is of interest to actually compute the forward solution are the boundary surface, hence the name boundary element method. So this is this is essentially the forward problem is a problem in numerical mathematics and based on an equation from physics that says, okay, you have this potential here at this location in space. What is it at a different location in space? You can then build in 3D models using, of course, known conductance properties. So you have to fix some conductance properties to compute what is the potential that should be detectable at the level of the scalp. And this is how you get, so I don't think I have a picture for this, actually how you get from oops, sorry, my computer is a little slow. How you get from a representation like this to a representation like this. Yeah. So here's something inside the brain. Then you have a differential equation that describes how this is propagated, and then you need to solve this differential equation given the known conductance properties of brain and skull to get to that. To formally introduce that, of course, would now need a digression to partial differential equations, which we will not do. Questions about the forward problem? No. Another view to view the forward problem is essentially as a model formulation in the sense of GLM. So, think back to the winter term when we talked about the GLM, where we had a design matrix and then we set the data. Y arises from the design matrix times some unknown beta parameters, maybe under the addition of noise. And here the analogy would be that the forward problem tells you, given certain parameters, which are the activities of the sources, what your expectation for the data is. So Y would be the electrode potential at the scalp. And now you are given the electrode potential at the scalp, and you have to compute the parameters, that is the activities of your sources, under the constraints of the forward problem / under the constraints of the design matrix. And that means that the logic for inverse problem solutions is fairly close to the logic of parameter estimation. So you have some data, you have some constraints, which is the forward solution, and you want to estimate some parameters. So essentially, it's a probabilistic model inversion with the forward solution as data prediction. Yeah? So the forward solution says if things are like that, then it looks at the electrode level like that, although this had needed to be computed. And now you want to go back to in the other direction. So you have to optimize some model parameters to match the observed data. What are the parameters in this case? Now we're leaving again the GLM. The parameters are the dipole locations and moments, and the moments referring to the orientation of the dipole and its amplitude. And the problem of this whole thing is that we are not in the GLM world, but we are in the world of EEG source analysis, where the forward model is actually non-linear in the dipole location, but linear in the dipole moment. This means if you change the location of some source activity, what you get on the scalp depends non-linearly on where your source activity is. But if you increase the activity of a given source, then what you get on the scalp without changing the position just also increases. in a linear fashion. And depending on, of course, the projection of the dipole. So the dipole orientation changes, of course, completely what you get on the Skype surface, but it changes it linearly. And we will see more pictures. So these are more kind of memorization slides in a second. So more pictures in a second. The difference between these two approaches is, again, that the ECD, or equivalent current dipole approach, uses a small set of dipoles which are variable in position and moment. So here you actually have to always compute the forward solution again based on the change in the dipole location, which makes this not necessarily easy to estimate because you have this nonlinearity in there. The other option, again, is the distributed source reconstruction, where you have many dipoles, but you actually have too many for the amounts of data that you have. Here you only need to compute the forward solution once, because you have computed essentially for every place in the brain. You could, of course, also do that in the current dipole approach, compute it once and then always look it up if you're at a different position. The problem with the distributed source reconstruction is that you have more parameters in terms of moments of the dipoles than you have actually data points. So this is why you need constraints there. So let's make this a little bit more clear by using some a little bit formalized approach. So this looks somewhat familiar to what you are familiar with from the GLM. So here you have a vector of electrode potentials. So if, for example, you have 64 electrodes, that means you have a 64-dimensional vector at a time t. So think again about the picture that I showed you in the very beginning about the ERP data matrix. So this would be one slice. Yeah. And the single dipole electrode data model involves a dipole position dependent lead field matrix. Here, this is this LU. This lead field matrix has as many rows as there are electrodes. Think about the matrix product. So this is 64 rows. So then the lead field matrix also, if you have this product here, also needs 64 rows. And it's dependent on the dipole position. Yeah? So if you put the dipole somewhere else, how a certain dipole moment, which we'll see in a second, is projected to the electrode level changes based on the location. Yeah? So if you have, think about it here in the brain, if you have some dipole sitting where now the mouse sits, of course, or the cursor here, you will have a different prediction from what you get at the scalp from when the dipole sits here. So this is depending on the dipole position, U, and it's actually nonlinear dependent on that. What you can see nicely in this equation is the linearity. Now, if you think about the dipole moment, which is a three-dimensional vector, so it talks about the activity of the dipole in the three directions. So, for example, if it's completely just pointing upwards, then it has just a component in the z direction, and the other two directions are zero. But of course you can have also tilted and whatever. You have to think that these dipoles, they model the pyramidal cells, right? So the pyramidal cells, of course, they change with the cortex folding, and a dipole represents a population of pyramidal cells, and they are represented in terms of the activity and orientation. And then the model is as simple as shown here. If you have computed your lead field matrix for this position, then you multiply the lead field matrix, which is 64-dimensional, for example, times 3, with the dipole moment, and then get your observed data. Yeah? Which also means that the columns of the design matrix actually represent the lead field matrix, but it's very close. The columns of the lead field matrix represent the activity, the electrode potential that you would have for a dipole that is of unit size in either the X, Y, or Z direction, right? So if you have a dipole that is 1, 0, 0, then this will select the first column of the lead field matrix, and then this, so you multiply it, then you have at the electrode level, you have essentially the first column of the lead field matrix, which is just, that's then the meaning of the lead field matrix columns, that this is the electrode potential you get for a dipole that is unit in either X, Y, or Z direction. Yeah. So this kind of single dipole electrode data model, this is actually, although might be a little bit confusing because this is called dipole, this is actually the same in equivalent current dipole and source reconstruction, distributed source reconstruction. Yeah. So that's completely identical. The question is now, do you try to explain your actual observed data with a few dipoles that linear superimpose in this case, or do you use not a few dipoles but dipoles at all different locations where you don't have to estimate this U parameter anymore? That's the difference. But the dipole model between equivalent current dipole modeling and distributed source reconstruction is the same, and it's the one that I show there. If you want to know many more details about this, actually look into my paper with Ludger from 2016, where we discussed the DCM EIP approach, and we have also quite a lot of stuff on the dipole modeling. So that's kind of the general stuff. And now let's look a little bit more into equivalent dipole modeling versus distributed source reconstruction. So now maybe with more pictures, less text and less formulas. The idea is, again, that we have these pyramidal cells that make up these dipoles on the cortical surface. If they are shown in neuroimaging, they're usually shown like kind of these oriented sticks with some something that fixes it somewhere, and then it has some orientation. So yeah, this yellow thing there, I hope you can see that. There's an arrow pointing towards it, so you might have a rough idea of where in the picture I'm talking about. And then you have to think, if there's a single dipole that has a certain orientation, this is projected to the scalp, and what you observe on the scalp is a topography of voltages. Again, this is for a single time point, yeah, so don't think about time at this point, or think of a single time point. And then depending on how the dipole, where the dipole is and how it is oriented, you see different things. And here, for example, this you have this clear dipolar pattern where you would think that somewhere under this on the scalp, you have the negative pole of the dipole here and the positive pole of the dipole here. Now, I visited the Phil once because I applied for postdoc, wanted to start an application for postdoc thing, and that then went its way, not really successful. But I sat in the methods meeting with Carl Fristen and everyone else, and we discussed EEG FMI integration, and so we also discussed EEG. And the question about EEG and FMI integration and knowing where the location is. And then there's something that I learned and that Carl Fristen taught me firsthand. The question about what is important in terms of a dipole and its moments versus its location. And this also gives some intuition for what we see on this page. So you can think of this business with the dipole and the electrodes as follows. You have a balloon and you have like a candle inside the balloon, or some little light bulb or whatever that has light on one side and not on the other. And then the question is, what do you see at the scalp, and then of course you can think about moving not changing the orientation, but moving it a little bit. You would think that what's happening on the scalp doesn't change much, because the light is projected very similarly. But if you change the orientation, then of course, even if you leave the location at the very same point, of course things will change dramatically. Yeah? So this is, I think, a nice image to think about this dipole business, and that's what I remember from my visit to the field. Which is something. In more kind of the Lux style of explaining how this fitting procedure works, it's as follows, and this is kind of what you can do using software solutions, and I think Bezer was a big thing doing this. So if you now have something like this observed, then you would put in, let's say, one dipole and suggest some location and some orientation. Then you have your current model of dipole locations and orientations. Then you compute what you would get on this scalp, and then you can compare it and see whether that fits or not. If it doesn't fit, then you would change basically the position or the orientation to make it fit better. Yeah? So again, now assuming that this is actually what you have on your balloon, and you have your little, maybe let's say, flash bulb, and you put the flash bulb in there, and you compare what you actually observed in terms of the EEG data and what your current flash bulb is doing, and you say, oh, it doesn't match well, then you change your flash bulb to make the two as identical as possible, and then you have fitted your parameters. So this is kind of a imaginative way to explain numerical optimization, in this case, usually using some gradient descent approach. And the story that I just gave you in terms of how much orientation and distribution affects, this is what you see here. So this is one orientation at a given location. If you only change the orientation of this dipole, you of course get a very different pattern. So the dipole orientation effect is larger than the dipole location effect in terms of fitting stuff. This shows the same thing again with a different picture. And then the thing is, of course, that what I just explained to you was for a single time point. Are there questions about this fitting and single time points so far? No, it's too warm. But at least in the summer, we don't freeze in here. Now the time domain is gone, so what can one do about temporal evolution? There are different things. One way is that one fixes the dipoles, so that one fixes the location and orientation throughout the period of the ERP that one wants to explain, and just lets the amplitude vary. This is basically the stuff that is done in DCM for ERPs, and the stuff that we did then in rewriting DCM for ERPs in 2016. Another option is to have rotating dipoles where the orientation and amplitude varies, so that you have, for example, an activity in primary somatosensory cortex, and you assume, okay, it will remain there, but it will change its orientation because it's going to a different bank of the cycles or so. So it also might make sense to let the amplitude, let the orientation vary. Of course, that doesn't mean that you think that the pyramidal cells change their orientation, but that the rough region where your dipole is active, another part of pyramidal cells which are in an orthogonal, in a mirror symmetric manner oriented, they become active. Or you can have moving dipoles where I guess one can also argue for, but it's It's a little bit strange when you have moving dipoles that also change the location. So to show you what you can do with a fixed dipole approach, so this is some visual activity here explained with 6 dipoles. And then you can you fix the dipoles and try to estimate the respective dipole activity, meaning their moments at each moment in time, to then make some claims about when certain parts of the brain become active. So here what you see is, I think it's most sensible to focus on 1 and 2 and then later ones. So these 1 and 2 and 3, they are fairly much located in early visual areas. So that's kind of lateral occipital cortex. 1 is in more calcarine cycles, and 6 and 7, they are more in parietal cortices. Now, if you fix them and just let their moment vary, then in this example, you see that these early ones capture EEG activity around 80 to 100 milliseconds, so definitely picking up, or mainly picking up P100 activity, and then the ones that are located more in parietal cortex pick up more activity that's happening later. Here 106, yeah, there would be N140 more. But so the idea is that by looking at the activity of dipoles over time that are fixed, that you somehow can do a spatial-temporal get a spatial-temporal representation of the stuff that you have on the scalp. So that shows essentially the same thing. So I'm skipping that. Before the break, let's briefly talk about the advantages and disadvantages here in apostrophes, because it's just a data analysis method, and of course it's not the best one, but it's also not the worst one, like any data analysis method. So an advantage of using equivalent dipoles is that it's very parsimonious. So you basically assume with each dipole you model a pyramidal cell population, and it's very parsimonious. You basically just say, okay, in this visual evoked potential, when in this time between 0 and 200 milliseconds, there are, let's say, 3 regions in the brain active, and the rest of the brain is inactive, like usually, because we only use 10% of our brains. I shouldn't say that, I have to delete this from the video. I don't know where this 10% stuff, and normally we don't use anything, and if we use this, we use 10% because we use 1 dipole in our brain. Yeah, and it's so that's from the level of parsimonious. It's nice, and it's very good for characterizing early sensory responses. So early sensory responses are actually nicely captured by these dipoles, because I think one of the reasons is that at that point, when you have just a flash of light, when you're looking at a flash of light, or and so on, then this primary sensory cortex activity is so dominant with respect to all the background activity, so that it's really nicely captured by a few dipoles. Disadvantages is, especially in the old ways, I remember doing that in Tübingen, basically in a GUI-based manner, because I was told to, where the aim was somehow to fit the dipoles so that they are where they should be, like in some other sensory cortex, I think, in this regard. But it was kind of dependent on where you initiate this thing. And then some of the aim was to click until you find a starting position, so that after convergence, the dipoles are where they should be. That was very weird. But this is the thing, that the final solution based on the dipole parameter initialization, where you put your flash bulb first or whatever, and then of course you could do different initial parameter choices, or use FMI activation as starting values. And then, of course, the question is, and that's of course a question is, how many dipoles should you use? No one knows. And in the general way of how this was done with respect to explained variance, there was no model complexity penalty. This is why they at one point came up with this variation of base equivalent dipole thing, where you then have a complexity penalty. Yeah. And one of the problems with equivalent current dipoles is if you have these non-dipolar topographies, which you always have for the Slater points, where you cannot, just by looking at it, cannot easily say, okay, I think that would be 3 dipoles, but you have kind of uncharacteristic topography, then also dipoles usually don't have much. Good. I think it's time for a break. Any questions right now? Good, then let's have a break, and after the break, discuss distributed source reconstruction.